Hello, everyone. My name is Jiang. I'm a senior research scientist at Google Research. Today, I'm more than happy to present some of our recent work on robust learning and its application. This is for the workshop on Weekly Supervised Learning 2021 in conjunction with the ICLR conference. Before getting started, I would like to briefly introduce my background. So my research area is in multimedia, which is in the interdisciplinary field of machine learning, natural language processing, and computer vision. And my research goal is to solve the real problem on big multimodal data. The number one lesson during the pandemic is to stay healthy and robust. So does the model. When we train a deep neural network, we also hope it to be robust. But why robustness is so important in deep learning? This ICLR 2017 paper, best paper, may shed light on this reason. So basically, Jiang shows that deep neural networks are very good at memorizing the noisy label. No matter how much noise do we have in the training data, we can always train a perfect model with zero training loss. However, if we look at the test error, as shown in this figure, where the x-axis represents the noise level, where the y-axis represents the test error, we can see as the noise level increases, the test error increases considerably. So that means the noise, it will hurt the generation performance when we have the noise label in the training data. So in our work, our goal is to pretty straightforward. So we want to learn a robust deep model on imperfect training data such that it can generalize well on the perfect test data. So what do we mean by imperfect training data? In fact, most real-world training data are not perfect. In today's talk, we're going to look at the three typical imperfect training data. First, if the training data has some noisy label. Second, the training data is either limited or insufficient to train a good model. Third, the training data has some ill-shaped distribution, such as a long-tail distribution. In today's talk, we're going to cover three topics. The first, how can we deal with the noisy label in the training data, including its methodology. Second, we're going to look at the key application in machine translation. And then we're going to look at some other application in the computer vision field. So first of all, let's look at some result methods dealing with the noisy label. This is based on the two papers we published recently. Okay, so we all know that to train a better deep neural networks, we need big data. However, if you look at the real-world big data, noisy labels are inevitable in big data. That also applies to text data. For example, in this Adbr review data set, we find there are a lot of noisy label. There's a mismatch between the review comment and review read. If we think about it, the noisy data creates a paradox for deep learning. On one hand, we need big data to train a better deep neural network model. On the other hand, the deep networks model can memorize the inevitable noisy labels in the big data, which could undermine the model's generation performance. So that leads to a critical issue. And for this research, we want to tackle the following problem. Given a noisy dataset of some unknown noise level, can we learn a robust deep neural networks model that can generalize well on the clean test data? Well, the challenge here is how can we overcome the memorization issue in the deep neural networks? Although there are some very good works that have been published at that time dealing with the noisy label, few of them are designed for deep neural networks model, and we know that memorization issue is a typical issue for deep neural networks. We may not experience such issue in other models such as SOM or decision tree. So we tackle this problem based on a theorem called curriculum learning. Here's some background. Curriculum learning is a learning philosophy proposed by Professor Yashar Bendu and Professor Daphne Nicholas' group around 2009 and 2010. It mimics a human cognitive process in which we do not learn things at random, but instead we learn examples organized in a meaningful order called curriculum. A typical curriculum would first cover an easy aspect of a task and then gradually transit to more complex aspects of it. For example, when we study math, we first need to understand what is 1 plus 1 before we move on to learning some advanced topics such as algebra. Similarly, randomly shuffling the example with correct and incorrect label would only confuse the model. But if we have a teacher who can determine the time-varying weight for each example, the students are expected to learn better. Ideally, the teacher would put bigger weights for clean labels and smaller or zero weight for noisy labels. Now the question is, how can we get this teacher, or equivalently, how do we get the curriculum from the teacher? To understand that, we need to look at some automation formulation for the curriculum learning. This is one of the formulation we can have based on one of our published work in 2015. In traditional machine learning, we optimize the model parameter W over some loss function L defined over the input data. In curriculum learning, we add a new latent variable V, where each VI is for each example to weight its loss. And we optimize the model over both the model parameter W and the latent variable V. To form a valid optimization problem, we must add a regularization function over the latent variable here called capital G function. So for convenience, we can simplify the notion a bit using the formula. Let's pay attention to the two newly added terms, that is, the weight variable V and the regularization function capital G. For each regularization function capital G, we can find a scheme to compute its optimal weight, V star. For example, if we set the capital function G as a negative L1 norm of the weight variable V, then we can get the famous self-paced learning function. So it computes the optimal weight V star in a straightforward way. So to be specific, if the loss for the S example Li is smaller than the threshold, some threshold, then we give it 1 weight. Otherwise, we give it 0 weight. So that means this scheme favors the example with smaller loss. So in some cases, we can also call how we compute the optimal weight V star as a weighting scheme. In fact, many works have been proposed since then to define curriculum as a function, either by specifying the function as a regularization function capital G, or directly define with how we can compute the optimum weight as a V star. That includes some famous ones such as self-paced learning function and the focal loss function. Nevertheless, in all cases, the curriculum is represented by a function. So in this work, we are wondering, can we learn a curriculum by a neural network directly from the data, where the input of the neural network is a mini batch, where the output of the network could be the weight for each example in the mini batch? That brings us to our work called MentorNet. So during training, we pick our favorite network called StudentNet, and during training, the StudentNet will extract some feature from the mini batch and send it to a new network called the MentorNet. The MentorNet will then output the weight for each example inside the mini batch to regularize the training of the StudentNet in the training stage. At the test stage, then we remove the MentorNet and let the student to make the prediction by itself. So in this paradigm, each curriculum is implemented by neural networks called the MentorNet. So in this work published in 2018, we mainly answer two questions. First, how do we learn a MentorNet? Second, since the existing curriculum at that time were optimized by batch gradient descent, which is not compatible with the mini batch training. So the second question is, how to apply curriculum learning in a mini batch training mode? So to answer the first question, in this paper, we propose two ways to learn the MentorNet function, where we can either use the MentorNet to approximate the existing predefined curriculum function, or learn novel curriculum directly from the data, given that we have a small data set with a label. To answer the second question, we propose a novel mini batch algorithm for efficient training, where we theoretically show some of its nice convergence properties. So now we find our first ingredient in our deep robust learning recipe, that is example revealing using curriculum learning. We verify our method on the large noisy benchmark called WebVision. WebVision uses the same validation set as the ImageNet 2012 on the same 1,000 classes. Well, the difference between WebVision and the ImageNet is that WebVision training images are automatically crawled from the web without any human inspection. So the training label bound to have some errors. In total, there are 2.4 million training images with noisy label. And the goal of this benchmark is to understand the gap between the model trained on the noisy label versus the model trained on the clean images defined in ImageNet dataset. So we train our model on the noisy training dataset and test it on the ImageNet validation set. Our model achieved pretty promising results in top 1 accuracy compared to the compatible baseline method in 2018. Now looking back, our work makes 2 impacts in this research direction. First, it demonstrated an effective way to overcome the memorization effect in deep neural networks, which inspired hundreds of different methods to tackle this problem together. So after this, there has been a lot of good work that tackle this problem from different perspectives, including the example weighting, and also label cleaning, label correction, pseudo labeling, and also using some data augmentation techniques. There are more here. We don't have time to cover all of them, but there has been great progress in this area. The second contribution is that we show a new way to learn curriculum and learn a data-driven curriculum and lay a foundation for other type of data-driven curriculum learning approaches. For example, a sub-area is developed to study how we can train this data-driven curriculum better using the meta-learning model. It is great, right? So much progress has been made in this direction, but what's missing? So one prominent issue we found in this direction is about the dataset. Existing dataset conduct a controlled experiment on synthetic label. So what we mean by controlled experiment? So we mean that for each model, we want to evaluate that on a spectrum of noisy level ranging from, say, 20% to 80%. Performing the controlled experiment is very important because in reality, we do not know the noisy level in the training data. Hence, we hope our model is robust across all possible noisy levels. Well, the problem is using the synthetic label. To create noisy benchmark with controlled noisy level, so people are adopting a very simple strategy to create this using synthetic label. That is, for each example, we just randomly flip to a different label. So the use of the synthetic label leads to 2 critical issues. The first one is about contradictory funding. For example, even for a basic question like whether deep neural networks are robust to massive label noise, our community gives 2 opposite opinions. Either deep neural network is vulnerable to label noise or is robust to massive label noise, by Ronick, for example. So why do we see this contradictory funding? This is because these studies all use synthetic label noise, and there exists multiple artificial ways to construct this synthetic label. A slight change in the setting when constructing this synthetic label would lead to dramatic different results. More importantly, we find that the method that perform well on synthetic label noise may not work as well on realistic label noise. So these 2 issues motivate our new work to move beyond the synthetic label noise. So the first thing we want to address is about the dataset. To find some realistic label noise, we just use the web. And to do that, we use the class name in each dataset and using Google image search to search the class name. After that, we manually annotate the top 1,000 returned images, and each image is annotated by 3 to 5 workers. Then we utilize the web images with incorrect label, such as this one, and use them to replace the image in the original dataset according to some predefined noise level. In doing so, we use the web image as a realistic proxy to the real-world label noise and put that into the dataset. To support future research, we established the first benchmark of realistic and controlled label noise by manually annotating about 200,000 images. This benchmark can be used to compare synthetic and realistic label noise over multiple noise levels on two tasks, source classification and fine-grained classification, and also can be conducted in different settings, for example, training from scratch or fine-tuning from train checkpoint. The datasets are publicly available for reproducible research. So for the naming, we employ the concept from the Matrix movie, and we call the realistic label noise as a red noise, and the synthetic label noise as blue noise, to make comparison to the blue pill and the red pill in the Matrix movie. Well, the following figures show some comparison between the synthetic and the realistic label noise. Where we see in the first column here that represents the true positive for each class. Here we have two classes, Ladybug in the mini ImageNet dataset and the Honda Accord in the Stanford card dataset. Where this second column marked in blue represents the synthetic label, and the third column marked as in red represents the realistic label noise. So as we see, there are three notable distinction between the image with synthetic and realistic label noise. First, image with realistic label noise share a highest degree of similarity with the true positive images. For example, the synthetic label noise label for class Ladybug could be anything, such as a dog that looks nothing like a ladybug. In contrast, the realistic label noise are more similar and include more similar looking bugs. Second, realistic label noise can come from open class vocabulary outside the class vocabulary that is defined for the classification task. For example, while the synthetic label noise can only be 1 out of 100 class defined in mini ImageNet, realistic label noise can be anything, such as this ladybug cartoon character, which does not include in the vocabulary. And in the last but not least, realistic label noise is at the instance level, meaning that the noisiness for each image varies based on its content. For example, the noisy image for car images are often taken from a side view instead of either from the front or the rear view. This is because from the side view, it is more confusable as the car brand logo and name are often not visible from this view. On the other hand, the synthetic label noise is class conditional. In other words, the label noise is independent of individual image content. So based on those differences, we can expect there must be some differences between their property when we do the experiment. Now, to address the second issue, which is about the method, we propose a simple but effective method called mental mix to overcome both synthetic and real-world noise label. How? By adding more gradient to our robust learning recipe. Before introducing our method, let's quickly review a data annotation method called mix-up. Let's consider two images randomly sampled from the dataset, X and X prime, along with their one-hot label Y at 1 prime. So mix-up just do a simple average between the image in their pixel space and create a new image. Similarly, we can average their one-hot label to create a new label. So the weight, lambda, used in the average is sampled from a beta distribution. Why does it work? The theory behind the mix-up method is Versino risk minimization. In conventional empirical risk minimization, we minimize the expectation of the loss over a delta distribution, where we only put the probability mass over some observed example in the training data. In Versino risk minimization, the expectation is minimized over a so-called vicinity distribution, PV. It smooths the delta distribution by putting more probabilistic mass between examples. For example, if we define the vicinity distribution in the following format, then we can recover the mix-up method. Here, we find our second ingredient in our robust learning recipe, data augmentation by mix-up. So following the similar idea, we can extend our curriculum learning approach from minimizing the empirical risk to minimizing the risk defined over a new vicinity distribution. Let's skip the math and theory and get straight to the method. So the result method is called a mentor mix, consisting of 4 steps: wait, sample, mix up, and wait again. As shown in this animation, in the first step, for each example in the mini-batch, we pass it to student.net and then to the mentor.net to compute a weight for each example. So we normalize the weight into a distribution. In the second step, for each example in the mini-batch, we sample another example according to the distribution to form a pair. In the third step, we mix up the original example with the sampled example to form a new example using mix-up. In the last step, we feed those new examples into the network to compute the weighted loss. So the last step is optional only for high noise level. And in backpropagation, we only update the student.net, not the mentor. So in a nutshell, the mentor mix applies 3 ingredients to create this robust learning recipe. First, example rereading. Second, data augmentation using mix-up. And the third, importance sampling. So here we compare our method with mentor mix method with some recent highly competitive method on the new dataset created by us. It is hard to read this giant table, but here what we do is we compare with different methods over different settings, including on 2 different tasks like coarse classification on mini ImageNet and the fine-grained classification on Stanford Card by training the model from scratch or fine-tuning from ImageNet pre-trained point. Of course, we compare that with different noisy tabs, including a synthetic label called blue and realistic label called red. And each cell here represents the average performance across 10 different noise levels. So take-home message here is that the methods that perform well on synthetic label may not work as well on realistic label noise, except for ours, which yield consistent improvement across all the settings. So on the Web Vision dataset, recall this is the performance we obtained using the previous approach. Our new method significantly improved the state-of-art baseline by about 3%. This result is significant as we know that 3% improvement on the ImageNet validation set is a significant improvement. So finally, we also conduct in this paper the largest study into understanding the deep neural network trained on noisy label. So our study presents some new findings that may challenge our preconception about noisy label. For example, if we compare the synthetic noisy label with realistic noisy label, we find that CNN generates much better on real noisy label and may not learn pattern first on the real noisy label. Due to the lack of time, please read our paper for more detail. Okay, let's move on to the next key application, machine translation. This is based on our 2 papers published in ACL 2019 and 20. So neural network translation model, neural machine translation model, or NMT, has achieved a great success in recent years. A typical NMT model consists of a transformer encoder and a transformer decoder. The attention module is used to pass the context information from the encoder to the decoder. Given a parallel sentence pair xy, we denote the target input as z, which is a shifted copy of the target sentence y in the NMT model. So the NMT model is trained to minimize the negative log likelihood of the sentence pair on the training purpose. However, we find that the neural machine translation model are very sensitive to the input. That means even a small perturbation in the input can dramatically change the translation output. Consider some example we take from a commercial translation system, where the input sentence is in Chinese, 他是一个老师，肯定要学生努力学习, which translates to, he is a teacher and definitely wants students to study hard. However, if we switch he to she, the translation becomes, she is a teacher and she must definitely study hard. The meaning has totally changed, from letting her student to study hard to letting herself to study hard. Here's another example. If we change 英文 with 英语, both being English, but then the translation output can be very different. So these results demonstrate that Even the best commercial translation systems are still very vulnerable to small input perturbation. Despite the fact that the NMT model are already trained on millions and millions of parallel sentence data, we believe this vulnerability stems from the insufficient training data that fail to cover all types of perturbation. So in this work, our goal is to improve the robustness of the NMT model. We first proposed a gradient-based method called the ADV-Gen to generate some adversarial example. We improved the robustness of the NMT model by applying ADV-Gen function twice, both at the encoding and at the decoding stage. So formally, our goal here is to find the adversarial sentence in the following set. Given an input parallel sentence pair x and y, our goal is to generate the adversarial sentence x prime in the following set. First, we want the x prime to be as close as the original sentence to return the semantic similarity. Second, we want the x prime to distort the model prediction to the maximum extent. So we designed an algorithm called ADV-Gen to find those adversarial sentences in the set. At the encoding stage, we have the following step to create a sentence x prime. To find the adversarial sentence x prime of x, we conduct the following step. First, we compute the translation loss over the original parallel sentences. Next, we use a bidirectional language model to find the top k similar word for every word in the source sentence x. The language model will be jointly learned with the NMT model. After that, we sample a word position from the source sentence. And finally, we replace the word at the sample location with a different word in its top k list. The search is guided by the gradient of the translation loss, so our model is a white box model. After generating the adversarial sentence x prime, as shown in the bottom right corner of the slide, we feed that as a new input sentence in order to a text encoder. To define the adversarial tag, we can use the same function ADV-Gen again to find the adversarial target input for the decoder. Here, we discover a new ingredient in our robust learning recipe, data augmentation by adversarial learning. So to verify the effectiveness, we conduct the experiment on standard benchmark for machine translation. So the result on the NIST Chinese to English translation show the introduction of our method leads to a substantial improvement over some classical models such as transformer model across different dataset, test fields, like a validation and test set. Specifically, our approach achieves an average gain of 2.2 blue point. For reference, in machine translation, if a method gets improvement above 1.0 blue point, that's considered a significant improvement. So here we are getting 2.2 blue points improvement over a very highly competitive baseline. On the another data set, WMT14 English to German translation, we can find a similar pattern where we achieve the improvement of 1.6 blue point over the state of art result at the time. To further verify our method, we compare with more method, more state of art method, and show in this table, we can observe a similar trend. And we also show that our method is compatible with the back translation model. Now, to verify the robustness of our approach, we add synthetic noise to the clean validation set. To do that, we randomly replace a word with a similar word according to the similarity of their wording value. We repeated the process in a sentence according to a predefined noise level, ranging from 0%, which represents the original sentence, to 15%, as shown in the x-axis of this figure. Now, when we compare different approaches, their blue score, as shown in the y-axis of this figure, and we see a consistent improvement of our method across all noise levels. And we also find that the improvement gap can become bigger with the growth of noise level. Now, looking back, I believe this work makes two impacts in this direction. First, we raise the awareness of this serious vulnerability issue in the neural machine translation model, and this insight leads many follow-up work research to solve this problem together. Second, we demonstrate that the adversarial augmentation can be used as an effective augmentation method for natural languages. And we observed that there are also some recent work that use our method as augmentation techniques for different problems in NLP, such as sequence labeling, pre-training, or textual attack. Now, after this work, we are wondering, can we improve the robustness even further? And so I think the answer is yes. So how? By adding more ingredient to our robust learning recipe. So let's bring us to a new method called ADVR, Adversarial as Augmentation. So this is based on the idea we want to redefine the distribution we want to optimize with a new vicinity distribution. So consider the example. So suppose this solid dot here represents the original example we have in the training data. That's a parallel sentence. And using our previous method, ADV-gen, we can generate the adversarial sentence in the discrete data space. Recall, adversarial sentence has similar semantic meaning as the original sentence, but can distort its model prediction. In the next step, then we can apply the mix-up between the two generated adversarial examples, represented by this dotted triangle here. So we do this mix-up in the embedding space and generate a sentence we call the virtual sentence, because we can only observe their embedding but not their actual word. So in the end, we employ the curriculum learning for the important sampling and then to compute the final loss. So in summary, for this method, its robust learning recipe includes 3 ingredients. First, data augmentation using mix-up. Second, adversarial learning. And third is curriculum learning and important sampling. So we verified this idea on the same benchmark we presented before. The first one is NIST Chinese to English translation. Here we can see an even bigger improvement where we improved the state of art by almost about 3 blue points. In particular, it significantly improved our previous result, ADV-gen, by a large margin. So this similar result we can observe on different data sets, for example, on this English to German and English to French translation task, where we see a decent improvement of 1.5 blue point over the state of art result at that time. Now, for the robustness experiment, here we show the result of our previous approach. Recall that the x-axis represents the noise level from 0% to 15%. The y-axis represents the blue score point, and the blue bar here represents our previous approach. With our new approach, we can see a significant improvement over all the methods across all the noise level. That means the new method exhibits stronger robustness against noise level. Now, let's look at the last subtopic. That's a robust learning application in computer vision. So recall our goal is to train a robust deep model on imperfect training data such that it can generate well on perfect test type data. And we have talked about 2 types of imperfect training data, noise label and limited training data for machine translation. In the following case, we're going to cover some of the more type of these data. And the first one is about image synthesis and or text-to-image synthesis. In this setting, we are given a class name or a natural language sentence, and our goal is to synthesize realistic-looking images. So current general generative adversarial networks or GAN model achieve a very impressive job in synthesizing image of high fidelity. However, the success of the GAN model heavily depends on the quality and the diversity of the label training data. For example, here we show the big GAN model trained on full ImageNet data for 2 classes, Goldfinch and the Bust. As we see, the quality of the output image is reasonably well. However, if we reduce the training data to 25%, the quality has vastly decreased. Because we often use the quantitative evaluation matrix called FID to measure the realism of the generated image. Lower the matrix, the lower the better. On the limited 25% training data, we can see the FID become much worse, almost double. To overcome the limited training data for the GAN model, in this work, we propose a robust learning recipe with 2 ingredients. First, using the data augmentation. Second is the model regularization. So model regression and new techniques we haven't discussed, but the general idea is pretty straightforward. We want to encourage the model to produce similar prediction for different copy of the same input. And using the techniques, we can get a state of art result on the ImageNet data, as shown in this figure on the right, where the x-axis represents the size of the training data from the 100% full data to only 10% of data available in training, where the y-axis represents the FID metrics, the lower the better. The orange curve represents our own method. As you see, we outperform the state of art result by a large margin, especially when the data is very limited. Now, let's look at another work that deal with the U-shaped distribution, the long-tail distribution. So in many real-world data sets, the number of training examples are not equally distributed. There exists tons of classes that have very few training examples. However, the fact that these classes have fewer training examples does not mean they are not important. On the other hand, they can be very important. They can be some rare event or accidents that we do want our model to do well. So here we develop a robust learning model to overcome the long-tail distribution. Our work is built on meta-learning model. So at a very high level, one can think of the meta-learning model as a more advanced approach to train the internet. The internet can be seen as one of the meta-learning models. Anyway, so this robust learning recipe for this method contains two ingredients. First, example revealing. Second, important sampling. So as this shown in this figure, using this robust learning algorithm, we achieve a very impressive result. First, we get a 3 times beta, as shown in this figure, where the x-axis represents the training time of comparing our model with the best, one of the best meta-learning model, where the y-axis represents the top-line accuracy on the CFAR. And we see that our method is at least 3 times faster than the current best meta-learning model. And then we compare our method with the very recent method on this long-tail distribution classification task on CFAR 10 and CFAR 100. Here it's very hard to read this giant table, but the take-home message is that we get a very competitive performance compared to the recent algorithm dealing with the long-tail distribution. And we found that this method is also very effective for dealing with the noise level. And remember, we have this new data set called control noise wave label. And here we conduct experiment on one of data set, the mini image net split. And we compare our method with very recent methods such as the mentor mix and the divide mix. We observe this new method get pretty impressive result across all multiple noise level, and on average gives you the best result. Now finally, let's look at the problem of another application, that's a future prediction in video. So in this problem, we are giving an observed trajectory of a pedestrian, such as this yellow trajectory here, and our goal is to predict where the person is going in the next 10 to 15 seconds, as shown by the heat map here. So as we can see, this problem is very critical in many industries for different applications. We may encounter different views of camera video of different camera views, such as a bird eye view from the drone, or maybe a dash camera view from an autonomous driving vehicle. So in this work, we are interested in training a single model using the simulation data that can be applied to any real-world video with various unseen camera views. Now the challenge here is how can we overcome this U-shaped distribution where there's some discrepancy between the camera view that's available in training and the test type. And another one notable challenge here to note is that because we assume like the camera view is unseen in training, so we cannot assume there is some certain camera view that's available at the test time. So we propose a method called SIM-aug as simulation and augmentation. So here's the diagram for the overall method. I don't want to dig into detail, but the method looks very similar to our mentor mix algorithm. containing 3 ingredients in this robust learning recipe. First, example revealing. Second, data augmentation using mix-up and adversarial learning. Third is about important sampling. So here's some visualization about our model to the prediction over multiple camera view from the Jiang top-down view and also from dash camera view on 2 datasets. And we find our method compared favorably against the state-of-the-art method in terms of the arrow, having the lower arrow in the prediction, future prediction. Okay, now let's look at some conclusion. So in this talk, we discussed several topics. The first is how we can use the robust learning method to overcome the noisy training level, and then use the robust learning method to deal with the vulnerability in machine translation model, and how to apply to other computer vision applications such as image synthesis, long-tail classification, and future trajectory prediction in video. So you may notice that throughout the talk, we are using the same ingredient again and again. Although personally, I do not believe there can be one universal approach that can deal with solve every robust learning problem. But there are they do share some similarity in terms of ingredient. And here's some ingredient we have gone over, and we want to probably recap some of those. The first one is example reading or using curriculum learning. So in this strategy, we can assign the weight for each example. So either by a neural network, such as MentorNet or meta-learning, or by specifying a closed form solution to compute the weight. So this strategy makes the model more robust to the example with noisy label. The second ingredient is a data augmentation using mix-up. So this will make the model, so we can do this mix-up either in the pixel space or in the embedding space as we do in the machine translation model. So this ingredient makes the model more robust to the holes in the data distribution between the examples. So the third one is data augmentation using adversarial learning. Here we talk about a method in NLP, but we do want to mention like there are also some very good adversarial learning techniques for robust learning in the computer vision field. So in this, generally, so this ingredient will make the model more robust to small but harmful perturbation in the input. So then we look at one technique called important sampling, where we use this to deal with the U-shaped distribution and make the model train faster. However, this is not a complete list of the very effective ingredient here. For example, there are some other very successful strategy, such as consistency or contractive learning for robust learning, or maybe there's another branch that's based on the pseudo labeling, either by doing this pseudo assignment or using some semi-supervised learning approaches. So in the end, I want to give a big kudos to all my collaborators, and the work would not be possible without them. And thank you. And here I'm ready to take some questions if you have any.